Let's make some force diagrams. This is the one that goes with force diagrams 1. You can ignore this 1A. All right. So the single most important, well, there's a few important. I was going to say the single most important thing, but there's probably a few important things that we need to know. I guess the single most important fact about forces that we need to know right now is that if something is at rest, of course that means it's not moving, or constant velocity, then both of those conditions mean that forces are balanced. And I'll tell you what, understanding that constant velocity goes with balanced forces is one of the single biggest hang-ups that people have in trying to understand physics. People don't like this. Maybe you don't like this. People want to think that if something's moving at a constant velocity, there must be some force in the direction that it's moving in. That is simply not true. Fake news. Not true. If something is moving at a constant velocity, the forces are balanced. Think about broom ball when you watch the teachers play broom ball. When that bowling ball was rolling through the no-touch zone, it just kept on going. I mean, the floor is a little wobbly down there, whatever. I just kept on rolling right through. Kept on doing what it was doing. Didn't speed up, didn't slow down, just kept on doing what it's doing. Why do I use a bowling ball for that game? Because the bowling ball is really hard, and the hard bowling ball on that floor, the way it rolls, there's like pretty much no friction. So that is why we used that particular piece of equipment. So constant velocity, the forces are balanced. If there was any unbalanced force, if you're thinking, okay, well, whatever, McGrath, but I know when my car is driving down the road, and I have the cruise control on, there is extra force in this direction. No, you are incorrect. There is force in this direction, right, from the traction of the wheels on the road, but there's also force in this direction. There's air resistance, and there's some like resistance from the axles and the, whatever, just kind of resistance. If there was extra force in this direction, then you would be speeding up. If there's extra force in this direction, then you would be slowing down. If you're going at a constant velocity, like you got the cruise control on, the forces are balanced. If there's extra forces, that's like tap, 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 tap with the broom, that makes it speed up or slow down. Okay, so draw a force diagram for the motionless cat on a rug. So all the things that we draw force diagrams for, we're just going to shrink them down to a dot. There's a cat. See how good an artist I am? It looks just like a cat. And what are the forces? So we are always going to have a force of gravity that is straight down. That is a force, and we're always going to label our forces in this way. It's a force of gravity. That's the type of force, comma. What's it on? It's on the cat. And what's the other thing that the cat is interacting with that's causing this gravity force? It is it's interacting with the, let's say from the entire Earth. I'm just going to say EE for entire Earth. It's not like the ground is causing the gravity. I don't want to say like Earth, like dirt. It's the whole Earth. That's why the cat's experiencing this gravity force. So that's the type. That's the victim of the force that's on the cat, and this is the other thing that's interacting with the cat, because a force is an interaction between two objects, always. All right, and then cat's not going anywhere, it's just sitting there, so forces must be balanced. There must also be one up like this, balanced. We call this a normal force. That just means like a support force that's perpendicular to. Normal, if you look it up in the dictionary around like the 4th or 5th definition, normal means perpendicular. There you go, who knew? So it's a normal force. This is a force diagram for the cat, so it's on the cat. And what's that from? You could say it's from the rug or the floor. I don't really care. I'm not going to pick at you for exactly what you choose there. All right. That's the first one. Force diagram for the skater is moving at a constant speed, so that means that the forces are balanced. So this, if you're gliding on frictionless ice, you might think that there's got to be a forward force. You are wrong. There isn't. So force of gravity, that is on the skater. You're totally fine to abbreviate these. That's cool with me. I'm going to do the same thing. Force of gravity on the skater from the entire Earth. Let's be consistent with that, though. Let's do that. And then there's a support force, our normal force. I'm just going to use capital N for that, on the skater from the ice. And that's all, folks. I know you don't like it. You want there to be a forward force, but there isn't. Now, if the skater was like pushing off with their skate, like to get going, if you've ever been ice skating, they kind of push off, I guess. And then there could, like, while that's happening, if they're like standing still and then they push off, then there would be a force in this direction, right? From the ice pushing forward, skate pushes back, ice pushes forward, and that's the thing. But not when they're just gliding like this. This is just like the bowling ball through the no-touch zone. That's it. If you're thinking to yourself, wait a minute, well, how am I supposed to be able to tell, looking at a force diagram, if something's at rest or if something's going at a constant velocity? The answer is you can't tell. That's not how you tell. That's not what force diagrams are for. All right. Force diagram for a softball player who's slowing down. Okay, that means, so if she's slowing down, then the forces are not balanced as she slides into the base. Label the forces and use equality marks of force vectors. So she's going this way, but she's slowing down. All right. So think about like the bowling ball going into the at the end of the course, going into the box. Think about how that worked. So force of gravity on the softball player from the entire Earth. There's a support force. I'm going to call that the normal force from the on the softball player from the ground, dirt. I don't think that this isn't really entire Earth because it's just they're just kind of scraping along the ground there. Now they're slowing down, so if she's moving this way and slowing down, that means the force on her, the unbalanced force, is this way. Now, if that messes with you, if you're like, wait, she's going this way and the force is this way, think about the bowling ball at the end of the game. As the bowling ball is rolling forward, if you want to slow it down, you got to go tappy, tappy, tappy backwards, right, to slow it down. What do you think your brakes are doing in your car when you're pulling up to that light in front of Walmart? You think the brakes are exerting a force forward on your car? No. You could try mashing on the brakes and the gas pedal at the same time. Not recommended. Actually, don't try that. Don't tell anybody I told you to do that. Get in big trouble. So the force is the other way, opposing motion. So this is a force. Her skidding on the ground, I would call that a friction force on the softball player, and that's also from the ground. Not equal to those. These are equal to each other. This is I don't know what. All right. How about a force diagram for a chandelier that's suspended from the ceiling by a chain? Okay, so this chandelier is a dot. It's not going anywhere. So that means the forces are balanced. Force of gravity on the chandelier from the entire Earth. And what do we call this, the one from the chain? You could call it support. It's not a normal force. Normal force is like when something is like resting on a desk or a floor or a car on a road or something like that, like a hard surface supporting something. That's not what's going on here. This is like a rope, chain, string, things like that we're going to call a tension force. Force of tension on the chandelier from the chain. That's kind of bad luck that those started with the same letters, so just wrote that out to make sure we're clear. and those are equal to each other because it's at rest. All right, force diagram for the bucket of water. It's being raised from the well at a constant speed. I know you don't like this, but that means the forces are balanced. You're like, but it's going up. But it's going up at a constant speed. If there was more force in the up direction, then it would be going up and speeding up. So I'm so sorry. I know you don't like it. And we're doing the force diagram for the bucket, not the person, right? So there's no, if you're like, oh, there's this force this way, sure there is on the person, but we're doing the forces on the bucket. The bucket doesn't know about the pulley and what's going on here. Bucket just knows that there's tension in that rope. So I got force of gravity on the bucket from the entire Earth, and then I got a tension force on the bucket from the rope. And those are equal. You're like, yeah, well, how are you supposed to know if it's going up or if it's just like at rest or if it's going down at a constant velocity? The answer is you can't tell by looking at this diagram. That's not what a force diagram is for. It's not to tell you what direction something's moving in. It's to investigate the forces and understand that. So if something's moving at a constant speed, constant velocity, then those forces are balanced. About a skydiver who's just left a plane and is still speeding up. So we're just going to assume that the skydiver is falling straight down. Like we'll say they jumped out of a helicopter instead of a plane. That makes it a little bit less complicated. So they're just falling straight down. And they're speeding up. Okay, so if they're speeding up, well, gravity doesn't care what they're doing. Force of gravity on the skydiver and the entire Earth. But when you jump out of a plane, you're going to start going pretty fast, and you cannot, in lots of situations, we're going to ignore air resistance. But when you're starting to go really fast, falling, if you fall for more than, 10, 20 meters or something, then you're going fast enough that you cannot ignore air resistance. So that's a force of air, basically a friction force, you rubbing against the air. And if you're like, yeah, but it's not like friction, it's not like rubbing against a hard surface. You ever seen a shooting star? You know what that is? That is a rock from space coming into our atmosphere so fast that its interaction with the air makes it burn up. So if you think that air isn't like friction, oh, it is. There's a guy whose name, he's an awesome name, Felix Baumgartner. If you know who that guy is and what he did, well, then I guess you know about him. If you don't, he is the guy who currently holds the record for jumping from the greatest altitude back to the Earth. He went up in like a weather balloon, and he jumped from so high, it took him 10 minutes to get, he like free fall for 10 minutes. And he was up in the atmosphere where it was thin enough that they were worried that he was going to start going so fast that he would actually burn up because he was going so they had to, it was very careful to not get him too high up. If you get too high, then you get going too fast and you're basically just like a shooting star. You just fry up coming back in too fast, too hot. So anyway, this person's still speeding up, going down. So there's force of air on the skydiver. What's it from? I guess it's from the air. So maybe I shouldn't call it force of air if I'm going to say that that's air. Maybe I could say that that's like a force of friction from the air. I like to use little f's for friction. I don't know why. All right. Force diagram for a skydiver who's descending at a constant velocity. That means forces are balanced. Now these are forces on the skydiver. So I got some, if you really want to, I would be okay with you doing force gravity on skydiver from the entire Earth. That's always going to be the same. I would be okay if you just made one like tension force from the rope, like kind of adding the ropes together. But really, each one of these ropes is making its own force. And these forces together are balancing out that down. You could imagine like if this was a tug of war and you got one kind of strong person over here and then 4 little kids over here pulling in these different directions, balancing this out. So I'm just going to put one label, but that's for all of these forces. Those are all forces of tension. I'm just writing arrows to those. Those are not forces. Force of tension on the skydiver from the ropes. And I'm not making, even though these 4 add up to this, I can't make a tick mark on this and this because those 2 aren't equal, neither are these 2, and so on. So can't do that. You don't always get to make the tick marks. How about ball rising in a parabolic trajectory? Label the forces and use equality marks on the force vectors. So here is the force of gravity on the ball from the entire Earth. You know what else there is? Nothing. And you're like, wait, but the ball's going up. Sure it is, but it's slowing down. And like, what is the other thing you think it's interacting with, like right now when it's in the air, in the up direction? Nothing. If you're like, well, there's a person who threw it. Not now, there isn't. The person threw it, but that person is not interacting with the ball anymore. These are the forces that are acting on it right now. So the only force acting on this ball is the force of gravity. Was there some other force like a little while ago? Yeah, sure. Is there going to be another force when it comes back and hits the ground? Sure. But right now, when it's in the air, the only force is that downward force of gravity. How about when it's at the very top of its trajectory? You know what the force diagram looks like then? Exactly the same as number 8. There's no force of motion. There's no force in the direction it's going. There doesn't need to be. So this is going up. What's this force doing down if it was going up? Well, it's slowing it down, right? That's like tapping the other way on the bowling ball. And then this force, gravity, of course, doesn't care what us humans are doing. It just pulls everything toward the surface. So what's going to happen after it goes up? It's going to get pulled back down. It's going to speed up. And the force diagram while it's going down will also look exactly like that. If it's going fast enough, there might be some air resistance. That's the only other thing that might be there. All right. How about on this cork floating in water? It's just sitting there. So, of course, there's the force of gravity on the cork from the entire Earth. And upwards, there's a, I'm going to put a B there for buoyancy. That's a buoyant force on the cork, and that's from the water. One up, one down, they're balanced. How about an airplane that's in straight and level flight? And we're going to assume, it doesn't say constant velocity, but I'm going to assume that it's going at a constant velocity. I don't know why this airplane only has one wing. That's kind of creeping me out there. I'm just going to draw another one here. There, that's better. Whew, that was close. It's kind of, that looks kind of, that needs another one of those too. Over there. That look better? I think so. Okay, so here's the airplane. Force of gravity, straight down on the airplane from the entire Earth. Is there like a forward force? Sure. There's a thrust force, like the air being pushed out of the back of the engines. That is pushing forward. The airplane pushes the air back, so the air pushes the plane forward. So force of, let's say, thrust on the airplane from the air. In particular, the air getting forced out the back of the engines. Now, it's going at a constant velocity, so the forces must be balanced. And even if these two are equal to each other, which they're not, they can't balance each other because they're not going, balance must be totally equal and opposite, or some other combination of angles. So what to do here. Well, there must be something here. What could that be? Well, the way airplane wings are designed, it forces the air over the top, and the same amount of air, if you had like, you know, a certain air density where let's say you got like 4 bits of air like this that are going to be split by the wing, then as the wing goes through, you got 1, 2, 3, 4, 1, 2, 3, 4. If you actually look at this distance here, because of the shape of the wing, these are a little bit further apart. And when the air particles are further apart, that's what low pressure is. Low pressure is like less air per unit of volume or space. So if these are closer together, that's higher pressure, and these are further apart, that's lower pressure. Things are naturally, well, if this is higher pressure, that's going to push up toward the lower pressure. So that means that that's how lift works. So this is the force of lift because of the wing cutting through the air on the airplane, and that is from the air pushing up. Okay? Up, down, balanced. Now, if all the forces are balanced, then must be something here too. What's that? Well, as the airplane cuts through the air, there's a lot of friction, just like, you know, if it was going really fast, it would burn up. And, you know, there was one of the space shuttle disasters. The shuttle, not the Challenger, but the, oh dear, can't remember the name. The one that burned up on re-entry. It was just going too fast, and the tiles on it that were supposed to deflect all that heat failed, and it basically did become like a shooting star, and lost some astronauts. So what is this? This is a force of drag, or you could call it friction, air drag, whatever you want. Force of drag on the airplane, also from the air. If you're looking at this thinking, wow, this airplane has a lot of interactions with the air. Well, it's an airplane, you know, I mean, it's up in the air, so, you know, all of the other forces, there's no, like, invisible hand that guides the plane through the air. You don't, I hope you don't believe things like that. My goodness, that would be terrifying. So all the interactions, all those other forces have to be interacting with the air because there isn't anything else for it to interact with. All right, this last one, this is kind of a little tricky. Draw a force diagram for a nail. It's been picked up by a magnet. So there's like some kind of magnetic force like pulling up on that nail. If you just did force of gravity on the nail from the entire Earth, and then you made an upward force that was equal to that, that would be fine. In fact, there's also like a contact between these two. So there's also like a force. If the nail is pushing up on the magnet, then the magnet must be pushing down on the nail at that contact point. Just as, you know, if I have two hands, if this one's pushing this way on this hand, then this is pushing this way. So if there is contact, then there is that kind of perpendicular support force. So in fact, there would be another downward force. That's a force, and we would call it a normal force because it's a contact perpendicular kind of force on the nail from the magnet. And then since it's not moving, there would have to be an upward force that's big enough to balance both of those. So I can't do any tick marks because this plus this would have to equal this. This is like 2 and 3. This would have to be 5 or whatever. And this would be the force of the... This is magnetic force, not something we're going to deal with at all, except for in this one little problem here, thinking about it. Nail, and that is also from the magnet. If you just made one up and one down, I'm totally fine with that, but in fact it would probably be more like this. All right.